Right now, in another universe, you made a different choice. You took a different job, said something you held back, turned left instead of right. And in that world, everything that followed, every conversation, every loss, every ordinary Tuesday morning unfolded differently. Not as a fantasy, not as a metaphor. As physical reality, happening in parallel to this one, right now, forever and accessible to you. This is not science fiction. It is one of the most seriously debated proposals in modern physics. And the disturbing part isn't that it might be true. It's that the mathematics we already use, the equations that built the atomic bomb, that power your computer, that explain the light coming off distant stars, may require it to be true. Let's start with what broke everything. In 1957, a 27-year-old graduate student at Princeton named Hugh Everett III submitted a doctoral dissertation that his advisor, the legendary physicist John Wheeler, spent months trying to convince him to shorten and soften. Everett refused. His idea was too strange to survive in half measures. Quantum mechanics, the theory that governs the behavior of particles at the smallest scales, had a problem. When a particle was observed, it seemed to snap from a fog of possibilities into a single definite state. An electron existed in multiple places simultaneously, until you looked at which point it chose one. Physicists called this the collapse of the wave function. They accepted it, they used it, they refused to explain it. Everett asked a simple question. What if the collapse never happens? What if, instead of the electron choosing one outcome, the universe splits? One branch for each possibility, and every outcome occurs, each in its own separate reality. In that case, there is no randomness, no mysterious collapse, just a vast, constantly branching tree of universes, each one as real as this one, each one unaware of the others. His colleagues rejected it almost immediately. Everett left physics, went to work in defense research, drank heavily, and died of a heart attack at 51. He never saw what happened next, because the theory didn't die. It waited. By the 1970s, physicists H. Dieter Zeh and Wojciech Zurek developed a mechanism called decoherence, a mathematical explanation for why the branching universes don't interfere with each other, why each branch feels singular and solid to its inhabitants. The math worked. It was tested experimentally. Suddenly, the many worlds interpretation wasn't a fringe idea. It was a serious contender. Today, physicists like David Deutsch and Sean Carroll argue it is the most mathematically consistent interpretation of quantum mechanics we have. But quantum branching is only one road to the multiverse. The second road begins not with the smallest things, but the largest. In 1980, cosmologist Alan Guth at MIT proposed that in the first fractions of a second after the Big Bang, the universe underwent a period of exponential expansion, a phase called inflation, stretching space faster than light could cross it. Inflation solved several deep problems in cosmology. It explained why the universe looks so uniform in every direction. It explained the large-scale structure of galaxies. It also implied something nobody wanted to say out loud. If inflation can start, it can keep going. In most regions of space, inflation stops, producing a universe like ours. But in other regions, it continues indefinitely, spawning bubble after bubble of new space-time, each one a separate universe with its own laws, its own constants, its own physics. This is the eternal inflation multiverse. Not a branching of possibilities, but an actual landscape of separate cosmic structures, each one born from the same inflationary mechanism, each one unreachable, each one potentially home to stars, planets, and things that have never had a name. Here is where the story becomes uncomfortable. For decades, physicists have noticed something strange about our universe. The fundamental constants, the strength of gravity, the mass of the electron, the cosmological constant that governs the expansion of space, are all tuned to values that permit atoms, stars, and life to exist. Change any one of them by a fraction, and you get a universe of formless particles, or instant collapse, or nothing at all. This is called the fine-tuning problem, and it has no good answer inside a single universe. But inside a multiverse, the answer becomes almost boring. If there are trillions of universes, each with slightly different constants, then of course we find ourselves in one where the constants permit life. There was no tuning, there was just selection. We are here because we can be here. The universes where no one could exist to ask the question, those exist too. They just contain no one to notice. Some physicists find this deeply satisfying. Others find it deeply unsettling because it suggests that the universe we live in isn't special. It's just the one we're in. There is no consensus. There may never be. By definition, the other universes are beyond our reach. No signal can cross between branches. No light can escape from beyond the inflationary horizon. We may be living inside a framework that is true and permanently untestable. Hugh Everett died in 1982, before any of this unfolded. His son later said that Everett believed, genuinely, that his branching versions were out there, that some copy of him had stayed in physics, had seen his work vindicated, had lived a different life. Whether he was right is something we cannot know. What we do know is this. The universe we can see, the one we measure and map and name, extends 46 billion light-years in every direction. It contains 2 trillion galaxies. It has been expanding for 13.8 billion years. And, if the physics is right, it is the smallest possible version of everything.